As I was telling you, for us to understand how to draw the waveforms effectively, we have to first understand how we will actually generate and transmit the signals. So we have the binary data sequence generator, our input signal. Then we will use a polar NRZ encoding scheme. All of us remember what is polar NRZ encoding. It will represent binary 1 as plus V. Ones will be represented and zeros will be represented with negative value minus V. And coming to the next block, this is a demultiplexer. It is a 1:2 line demultiplexer. The one single line input, every die bit pair which comes, say I have a die bit pair 1 0, it will send one signal to the upper line and it will send the second signal to the lower line. See, the first signal goes this side, the second signal comes below. It is going to split the incoming die bit pair into two separate bits. Okay, A1 of t and A2 of t. And each of these bits will get multiplied with quadrature carriers. The first quadrature carrier, phi1 of t, is root 2 by t cos 2 pi fct. And the second quadrature carrier is phi2 of t, root 2 by t sine 2 pi fct. And both get added to generate the final QPSK signal S of t. Okay. So the QPSK signal S of t will be transmitted. Now, as usual, this is the transmitter. So based on this, let us try to analyze how we are going to draw the waveforms. You can see, let's consider the binary data sequence as this. This is the sequence and we have divided it into pairs known as divids. Okay. First, the odd numbered sequence gets multiplied with a cosine. As you can see here, the odd numbered bits like first bit, third bit, fifth bit, they get multiplied with a cosine, and the even numbered bits get multiplied with a sine. Remember that. Odd bits which are separated by this dmux get multiplied with the cosine, and the even bits get multiplied with a sine. Okay. So please remember this. This is how I am going to write the representation here in the waveform. Let's write the first part of the signal, SI1 phi1 of t, the upper part. And one more thing what you should remember, a 0 will be represented with minus cos, and a 1 will be represented with plus cos. We are going to use minus cosine to represent a 0 and a positive cosine to represent a 1 in the odd numbered data bits. Okay, in the odd numbered data bits, this is how we are going to represent. And in the even numbered sequence, in the even numbered data sequence, we are going to represent 0 with minus sign. We are going to represent 0 with a negative sign and a 1 with a positive sign. Okay. Positive sinusoidal wave, plus sign. So accordingly, let's try to analyze. First thing what we are doing, once we divide this into die bit pair, we are dividing it into 2 bits. The odd numbered bit 0 is coming here, the odd numbered bit, and the even bit is going here. Okay. So the even bit 1 goes here, all the odd bits will come here, and the even bits are going down. Just like how the odd bit goes in the upper branch and the even bit comes in the lower branch. Odd bit gets multiplied with a cosine, even gets multiplied with a sine. So we will use cosine to represent odd bits and sine to represent even bits. Once we split this die bit pair into odd and even bits, And remember, each of these bits we will represent for a time period as required by the pair of bits, by the die bit pair. So whatever is the time required for 2 bits, that is the time duration of existence of a single bit now. So when I say odd bit, this odd bit itself exists for a time period which will be twice the bit duration, single bit duration. Okay, we call this as symbol duration. That's why I told you, remember, symbol duration in QPSK or memory PSK is different from the bit duration what we considered in ordinary BPSK. So what is a symbol duration? It is the duration for which the whole symbol exists. This is one symbol. One symbol has 2 bits. One symbol has 2 bits. So one symbol duration T is equal to 2 bit durations TB. Okay. One symbol duration T is equal to 2 bit durations TB. Now here we have, once we have split it into odd and even, we are going to represent each of these split up bits. The odd bit will also be represented for one symbol duration, and the even bit will also be represented for one symbol duration. Okay. So you can see here bit 0 is the odd bit. Bit 0 will be represented with a negative cosine. We know negative cosine means it should start at the negative maxima or the minima, whatever we call it as. At minus pi by 2, it will start, it will go to maximum, and it will come back. We have shown 2 cycles of carrier for our reference. Okay, there are 2 cycles of carrier shown. This is the cosine value representing 0. And if I have to represent 0, I have to use a negative cosine. The next odd, in the next die bit pair, the odd value is a 1. So I have to represent it with a positive cosine. If the bit is a 1, I should represent it with a positive cosine. Positive cosine starts at positive maxima, as you can see, and it will continue. We have shown 2 cycles. From here to here, 1 cycle. From here to here, next cycle. This is the representation for the third bit, which is 1. Next comes the fifth bit, which is also a 1. That will be again represented with a positive cosine. You see, it starts from here to here and continues. Wherever it starts, it should end there. So over a time period of T, the total time period is T seconds, which is equal to 2 bit durations. A positive cosine is used to represent a logic 1. Next comes logic 0 or binary 0 in the next die bit pair, the odd value. So this is the first, this is the third, this is the fifth, and this is our 7th bit. It's a 0, so I should represent it with a minus cosine. A negative cos, this is plus cos, this is plus cos, this is minus cos. So negative cosine means starts at the negative maxima and continues. So this is our representation for the coefficient SI1. Remember, SI can be written as SI1 phi1 plus SI2 phi2. It is split in terms of the first orthogonal sequence, which is a cosine, and the second orthogonal sequence, which is a sine. And this coefficient SI1 is what we are writing here. Similarly, the even numbered bits have sign to represent the waveform. So they get multiplied with a sinusoid. As you can see, the even numbered bits which come here will get multiplied with a sinusoid. So you see +1 from this first die bit pair, the second bit, this is the second bit, it is a 1. It will be represented with plus sign. Plus sign means which starts at, we know sign will start at 0 and 2 cycles of sine we have shown. Okay, this is the representation for the first bit in the first die-bit pair. Next comes the bit 4. This is bit 4. This is bit 2. The next even numbered bit is bit 4. And this bit 4 is 0. And 0 is represented with a negative sign value. Negative sign means this should be inverted. So this is negative sign. Till here, it is the next bit interval, which is minus sign. Okay. And the sixth value is again a 0. So the sixth value is also 0. And 0 should be represented with inverted sign. And we are going to invert. One more thing you remember. You will invert if there is a what? If there is a phase change between two successive values. Here there is no phase change. It is two continuous zeros. So I'll represent it with a continuous sine wave. And from here, once I finish this bit duration, I'll come to bit 4, or according to this die-bit pair, bit 8. Bit 8 is again a 0, and 0 will be represented with minus sign. But I won't represent it with minus sign because there is no phase change here. I have continuous sequence of zeros. It is a continuous sequence of zeros. So no phase change. No phase change means I should continue the carrier without any change. Carrier is continued without phase change. Please remember that. When will you show a phase change? When there is difference in the bits. Even here you can notice up. When I have a consecutive sequence of 1, it is a continuous signal here. There has been no split. And anyway, +1 matches that cosine also. That is a coincidence. But whenever there is a same bit sequence, there won't be a phase change. Only if there is a difference in the bit sequence, the phase change is visible. Finally, the QPSK signal will be the sum of these two. So as I told, the QPSK signal is represented with SI1 phi1 plus SI2 phi2. SI1 phi1 is this signal, SI2 phi2 is this signal, and this will represent the summation of both these signals. Okay. And coming to how to draw this summation, you have to take a little bit of care here. Usually it is easier if we notice the die-bit pair and the phase. So this is die-bit pair 0, 1. This is die-bit pair 1, 0. So adding these two signals is not so very easy. This is again 1, 0, and this is 0, 0. As you remember, do you remember the constellation? This would represent 1, 1, and the phase change is pi by 4. This would be represented with 0, 1, and the phase is 3 pi by 4. This point is 0, 0, the phase change is 5 pi by 4. And this point is 1, 0, the phase change is 7 pi by 4. And I think we called them as signals M1, M2, or M1, M2, M3, M4. We called these as the name of the signals. So if you notice, the first signal is 0, 1, which is an M3. So the first signal is 0, 1, and the next signal is M1, 1, 0. So from M3 to M1, can you observe? M3 is in the second quadrant and M1 is in the fourth quadrant. What is the total phase shift between these two signals? From here to here, it is 90 degrees, right? And from here to here, it is another 90. So the total phase change between M3 and M1 is 180 degrees or pi radians. 180 degrees or pi radians is the total phase change between M3 and M1. So what should I do? I will consider the basic phase of M3 and I will add pi radians to that. So what will happen here? What was the basic phase of M3? It is 3 pi by 4 is the basic phase of M3. To that, if you add pi radians, how much will you get? You will get this as 4 plus 3, 7 pi by 4. So I have to draw the waveform which starts and ends at 7 pi by 4. Before you understand how do you draw the corresponding starting and ending phases, let me show you the different phases for a sine wave. So in terms of radians, this is 0. This point corresponds to pi by 4. This point corresponds to pi by 2. This point corresponds to 3 pi by 4. Or if I want to write it in degrees, this is 45, this is 90, this is 135. Actually, 90 is of no interest to us. Anyway, this is pi 180 degrees. This point is how much? This will be 5 pi by 4 or 225 degrees. And this point corresponds to 7 pi by 4 or 315 degrees. And this point is 2 pi. So these are the, please note the points, especially the points. 45 degrees is this. This is 3 pi by 4. This is pi by 4. This is 5 pi by 4 and this is 7 pi by 4. Make a note of these points and accordingly you will understand the signals. I think I had drawn that. Yeah. See, how will a 45-degree phase shifted sine look, or how will the 45-degree shifted carrier look? It should start here. This is, it would have finished a quarter of its wave before. So the starting point of a 45-degree wave is 45 degree. It should start at the angle pi by 4 and it should end at the same point. It should not complete. So it has completed one cycle now. Started at pi by 4, ended at pi by 4. This is a 45-degree waveform. Similarly, how would I draw 135 degrees, or this is 3 pi by 4 wave? 3 pi by 4, if you remember, which is that 3 pi by 4 point? This point is 3 pi by 4. Yes or no? This point corresponds to 3 pi by 4. So if you see, this wave is starting here. This was 45. This earlier wave ended at 45. The new one which we are showing is 3 pi by 4 or 135. So it starts, both are in the same level. If you notice, the 45-degree line and the 135-degree line will be at the same level, right? So this is 135 and after this the sine wave is dropping. It will come, it should again maximize and again come and end at the same point, 135 degrees. You see, after maxima it will reach the point 135 degrees and it will end here. Okay. So this is the representation for 135-degree waveform. Similarly, a 225-degree waveform, you see, where is 225 degrees? This point corresponds to 5 pi by 4 or 225 degrees. So a given waveform should start here. It should start at 225. It should reach the negative maxima and then it should reach the positive maxima and again come down and end at the same point. See, 225-degree lines are same. Just like how 45 and 135 are same, 225 and 315 would be the same. Anyway, starting at 225, ending at 225, one cycle. And the last one is to start and end at 315 degrees. If you are starting at 315 degrees, you can notice which point is that. This is 7 pi by 4 or 315 degrees. So we should start like this, as you can see, starting, reaching the positive peak, coming down again and come and stop at the same level. This level corresponds to 315 degrees or 7 pi by 4. I hope now looking at these waveforms, it is clear how you have to draw carriers of different phases. So now again, we'll come back to this waveform and we'll try to complete this waveform. So as I was telling you, for the first case to represent 0, 1, I should write a waveform, a carrier waveform which has the phase 7 pi by 4. That means it is 315 degrees. So it is starting at a phase 7 pi by 4, and by the time it comes here, we have completed one cycle. So from here to here, it is one cycle. I'm using two carrier cycles. So again, I will repeat the same waveform and I will end up here. So we started at 7 pi 5 by 4 and we are ending at 7 pi by 4. We have represented the dibit pair 0, 1 now. Actually, in effect, this is the sum of these two signals also. Whatever signal we have represented here, this cosine and this sine, sum of those two is also given by the same waveform, which will have a phase change of 7 pi by 4 radians. Now, coming to the next dibit pair, I know between this 0, 1 and 1, 0, as I told you, there is a phase shift of pi radians. So there is a change of pi radians. So I have to shift this by a straight line. And from 7 pi by 4, if I should change by pi radians, minus pi if I do, moving in the anti-clockwise direction, I will usually subtract. Moving in the clockwise direction, we will add. So when I move in this direction and I subtract pi, from 7 pi by 4, I'll again get back 3 pi by 4. Therefore, the next dibit pair we are going to represent with a waveform which starts and ends at 3 pi by 4 radians. So have a look at the waveform, how 3 pi by 4 starts. See, this is 3 pi by 4, 135. It starts like this and ends here. If I want to repeat for two cycles, again it should start and end like this. You will notice the same thing. See, it is starting like this, ending here. Again, it starts here and ends here. This is the end point for this signal 1, 0. Okay. Starting at this point and ending at the same points, two cycles we have used to represent the second dibit pair 1, 0. Now you see something interesting. The third dibit pair is also 1, 0. So between this dibit pair and this dibit pair, there is no phase change. Both are same. Remember, I told you when both are having the same phase or both have the same value, there won't be any phase change. So what will I do? I'll continue with the same carrier. No phase change in this representation. Whenever the two values remain the same, no phase change. So continue as it is. So again, this will also have the same phase 3 pi by 4. You continue, you finish till here, again you continue and you end up. We finish two cycles to represent this dibit pair 1, 0, which is same as the previous. Okay. Now comes the last dibit pair 0, 0. Now between 1, 0 and 0, 0, you can observe this is 1, 0 and this is 0, 0. There is a phase change of 90 degrees. Between the values 1, 0 and 0, 0, there is a phase change of 90 degrees. And now our signal has ended at 3 pi by 4. This value is 3 pi by 4. And to reach this 0, 0 point, I have to add 90 degrees because the 0, 0 point is at 5 pi by 4. So what will I do? I will make a change from 3 pi by 4 to 5 pi by 4. So the starting point of the next representation would be 5 pi by 4. As you can see, I told you moving in the positive direction is add. So to this 3 pi by 4, if I add 90 degrees, I'll get 5 pi by 4. Whereas from 7 pi by 4, if I subtract 90, I'll get this. So all what you have to notice is the difference. The difference in the angle is 90 degrees. Since in the waveform, we had used 3 pi by 4, I have to add 90 to reach 5 pi by 4, whereas here I have to subtract. So please remember, from 3 pi by 4, if I add pi by 2, I will reach at the value 5 pi by 4. And the representation of the signal 5 pi by 4, you can see this one. 225 degrees corresponds to 5 pi by 4. Starts just before the negative minima, reaches the negative minima, and stops at the same point. You can see our signal also here. This last one is starting just before the negative minima. Till here we finished one cycle. From here to here, it is the second cycle. So we have represented the dibit pair 0, 0. This is how we draw the QPSK waveforms. So when I just mentioned it is the sum of these two signals, it is very difficult for you to directly add up these two. You will have to draw them point by point and add. Each one you should consider this points. You give some amplitudes -2, -1. Consider the point pi by 2, pi by 4, 0. And in the other signal 0, so on. You have to map them perfectly. Map this signal to this signal and add. That is more difficult. What I have shown to you is a much easier way of drawing the QPSK signal. Please try to understand this and try to do it for some more signals. If you have any doubts, you can get back to me. I will do some more examples and send it to you. Okay. So this is about the waveform representation. Next, we will talk about the reception of QPSK. We'll directly go to the block diagram. The QPSK receiver, I haven't put it here. Okay, let me just draw the block diagram of the QPSK receiver. It should have two correlators. Let me draw it here. As usual, we will receive the received signal comes here. Okay, that received signal x of t, we used to call it as x of t. It should be passed on to two branches or two sets of correlators. You know how to draw the correlators. In the upper correlator, I will use the first orthonormal basis function to multiply phi 1 of t. And for the second one, I will use the second orthonormal basis function phi 2 of t. And after the multiplier, I will have an integrator. Integration from 0 to t dt. Again here, integration from, remember, I should take one symbol time, 0 to t, not 0 to tb. So I integrate over one symbol time. This whole thing together is a correlator. Please remember. And once you have the correlator, remember you should have a decision device to which we give a threshold. So decision device, a threshold value will be fed to this decision device. And once it crosses the threshold, it makes a decision. If it is below the threshold, it will make a different decision. So here also we have a decision device and the threshold value is given. And the output of these two will be fed to a final multiplexer. You can write it as a square block or any block. This multiplexer will combine the signal coming from the upper one and the lower one to give us the dibit pair. So the dibit pair, which is an estimate of the transmitted binary sequence. Remember, we transmitted one binary sequence, a pair of 2 bits. We are going to recover the odd numbered bit here and even numbered bit here. Once you recover the odd bit and the even bit, you are going to combine again. So this is a 2:1 mux. We'll combine both together, first odd bit, then even bit, and the Divert pair output is available at the receiver. And that should be the best mapped sequence to the transmitted symbol. This is the receiver block diagram in what? In QPSK. Please remember the transmitter and receiver block diagrams are also commonly asked. Now coming to the, so I already told you what the receiver has. We'll directly move on to the probability of error derivation. We know we have an AWGN channel. The received signal is sum of transmitted symbol plus additive white Gaussian noise. As usual, I ranges from 1 to 4 and T lies in the range 0 to capital T. Then we have the two correlator outputs X1 and X2. See here in the block diagram what we have drawn. The output of the first correlator X1 is here. Output of the second correlator, this is X2. If this is X of T, this is X1 of T and this is X2 of T. Okay. We are finding these values by multiplying with phi1 and integrating. That's all we are doing here. You see here, output of the first correlator is received signal X of T multiplied with phi1 and integrated over 0 to T. And here, once we substitute the values, this will result. We are not going into in-depth analysis. You will have to just simplify. And remember, in-depth analysis is not required for you. Plus or minus root E by 2 plus W1, this will reduce to. And the second signal is also X of T multiplied with phi2 integrated over the time 0 to 2. This will result in minus or plus root E by 2 plus W2. This is plus or minus, this is minus or plus. Okay. And this W1 and W2 are normally noise factor N0 by 2 usually. Now, once we have this signal vector, the average bit error, okay, the average bit error of coherent binary PSK receiver. Remember, it constitutes, QPSK constitutes of 2 BPSK receivers. If you remember, each of these represents one BPSK receiver. If I have 2 such BPSK receivers in parallel, that gives me a QPSK receiver. So I can use the probability of bit error as for in-phase and quadrature path. This is the in-phase path. Wherever I use the cosine carrier, if this is cosine, this is the I channel, in-phase channel. And wherever I use the sine carrier, that is the Q channel or the quadrature path. Okay. So the in-phase channel and the quadrature phase channel are there. And now we have just like how we had defined in BPSK, we can define P dash as the probability of error, which is the Q function of root E by N0. Okay. And accordingly, we know that the decision device in the in-phase path will account for 1 out of 2 bits constituting one symbol of the Divert, and the decision device in the quadrature path takes care of the other Divert. So among 2 bits, 1 bit will come from the in-phase path and the other bit will come from the quadrature phase path. So average probability of a correct detection will result from the combined action of the 2 channels. So the probability of correct detection will be 1 minus probability of error in the individual channels. This P dash represents probability of error in each phase. In phase and quadrature phase, both will have the same probability of error. If I subtract that and square it, So for each in-phase channel into probability of error in the quadrature phase channel, and the correct detection will be 1 minus probability of error in phase, 1 minus probability of error in the quadrature phase channel, or a total of 1 minus probability of error the whole square, because PEI and PEQ are equal. This P dash represents both PEI as well as PEQ. Since both are equal, 1 minus both, 1 minus each of them will be probability of correct detection. Okay. So I have 1 minus the Q of, what was the value of P dash? Q of root E by N naught. So we have substituted this will, and once we expand it in the form A minus B the whole square, it will result in this. Finally, the average probability of symbol error for QPSK is 1 minus probability of correct detection. So if I have to use the combined probability of error for in-phase and quadrature phase, on an average level, the average PE or probability of error on whole for the QPSK is 1 minus probability of correct detection. So 1 cancels out. What is left out will be this and this. 1 minus 1, 1 goes off. So these two values are left. Okay. And because of negative sign, I'll have 1 minus 2q root E by N naught plus q square root E by N naught. Because of this minus sign going inside, this becomes positive, this becomes negative. And please remember, in the region where E by N naught is more than 1. So whenever we have the signal energy to noise ratio greater than 1, we can ignore this quadratic term or the Q square term, because its value will be very small. Error will be very less whenever I have a sufficient signal to noise ratio. So whenever SNR is higher, the error will be minimized. Therefore, we have probability of error defined only by the second term, which is 2 times of Q root E by N naught. And if you observe closely, you can clearly see that this value, whatever probability of error we are getting, is almost double that what we got for the BPSK system. And the simple reason I told you, we have 4 signal points in the same constellation or the same constant magnitude circle, where we used to have only 2 signal points. So the probability of error has doubled, as you can see. And the Euclidean distance, I already told you, the distance between the 2 signal points is root 2e. We already found that here. This one, root 2e is the distance between 2 signal points. So if we consider representing that Euclidean distance as d12 or d14, and if I substitute, the energy per symbol will surely be equal to twice the energy per bit. In one symbol, there are 2 bits. So energy per symbol will be twice the energy per bit. So I'll replace this E with 2EB. You'll get PE is 2Q of root 2EB by N naught. As I told you, which is exactly, this is also called the bit error rate or probability of error. It is Q of root 2EB by N naught. Therefore, QPSK system achieves the same average probability as binary PSK system. See here, whatever we had as 2 times, with gray encoding, what happens? This PE and BER, bit error rate, will become half of PE. The probability of error, whatever I had, becomes half when we use gray coding, when we use gray encoding. Remember, this is not true for other methods of encoding. Whenever we make use of gray encoding, that is with a single bit change from one dibit pair to the other. We have 1101000 and 10. These were our messages. Then this BER becomes what? Half of PE. So I'll have this as just Q of root 2 EB. Then I will have the same average probability of bit error as the BPSK system for the same bit rate EB by N naught, but the bandwidth used in QPSK will be just half of that used in BPSK. So please remember, QPSK is a more efficient system than BPSK. For the same signal to noise ratio, as you can see, and the same average probability of bit error, QPSK systems will transmit 2 bits of information where BPSK could transmit only 1 bit. Hence, QPSK gives you a better performance than BPSK in terms of bandwidth usage. And remember, we are comparing both for getting the same bit error rate and what? The same signal to noise ratio. So both BPSK and QPSK are compared to have the same bit error rate and same EB by N naught ratio. And this is how we get. And when we have to compare, that's why we will use gray encoding so that our bit error rate will be half of this average probability. Okay. Hence, we'll get the same performance, but we are transmitting double 2 bits where we would send only 1 bit in BPSK. So QPSK is more efficient. And next we will talk about a special case of QPSK, or the quadrature amplitude modulation, or MRE QAM, in the next class. Till here, including ASK, FSK, BPSK and QPSK and MRE PSK. All these things you should study for the internals. Thank you.